Hi everyone, I'm Richie. I work at Uber on the M3DB team. Yeah, and today I'm going to talk a little bit about kind of an experience I went trying to build a distributed time series database on top of existing tools, in this case FoundationDB. As everyone knows, the first rule of distributed system is roll your own. And I'm just kidding. Yeah, the gist of this talk is really going to be about, a lot of people at a lot of companies are building their own distributed systems. A lot of times you're just building something on top of something else. So you may be building an application on top of CockroachDB, but that application on top of CockroachDB is still kind of implicitly a distributed system, right? So if your application is deployed on more than one instance, basically, in some way, you have to reckon with some of these problems. And what I wanted to do was kind of explore the problem of, M3DB was started development like 4 years ago or something like that, maybe a little longer, and everything was kind of built from scratch. And what I was trying to figure out was if you're starting today and you're like, I just want to store like a lot of time series data and I want to ingest it really quickly, and you decided not to start from scratch and maybe leverage some of the existing primitives that are out there today, how far could you get and how quickly? I'm tech lead on M3DB, and I spent the last 2 years working on it, rewriting core parts of the storage engine, adding new features like complex types to make it kind of like a more general purpose time series DB, and just generally trying to optimize it for higher write throughput because we use M3DB to store like all of Uber's internal metrics. So it's kind of the opposite use case of CockroachDB. We don't care about transactions at all. We just have like this huge fire hose of data that we want to kind of store and persist durably. So the way this talk will go is I'm going to start off by explaining what I mean by high volume time series data, because it's kind of a vague term. Next, I'm going to talk a little bit about FoundationDB because it's the kind of the foundation that I built this prototype on. Next, I'll kind of dig into like the details of like how it works and how I built it. I'll talk a little bit about how this could be extended because it's just a prototype. And then, just some closing thoughts about FoundationDB and, how you can leverage those types of tools in your projects. So yeah, first big disclaimer, this thing is just a prototype. Don't use it for anything. If you look through the code, it's filled with to-dos, gotchas, missing features, cut corners. I barely wrote any tests. It was mostly a prototype to see if what's possible kind of with the tools that are out there today. So the first thing is the data model, right? What do I mean by high volume time series data? So if you've ever used any kind of modern alerting system like Prometheus, Datadog, SignalFX, whatever it is, if you're kind of emitting any kind of metrics out of your system, the API you kind of want to support is that, you have a series ID. So it might be like the P99 latency of some endpoint on your service. And then every once in a while, you're going to emit a tuple for that time series, right? You're going to say at time, 12:03 and 2 seconds, the highest observed P99 latency for this endpoint was 400 milliseconds. And you're going to write that as a value. And you just have a ton of these values that are constantly being generated because you're running, all your applications. They're constantly emitting all types of data, and you need to store and query that data. So the two APIs I care about are basically write series ID and then the value. And then given a series ID, can I pull back all the values over a certain time range? Things get a lot more complicated once you start talking about indexing, right? If you want to kind of search for all time series that match like a regular expression. But we're going to ignore that problem for now. Okay, cool. So what's so complicated about this, right? You're just like, can I just throw this data in Postgres or something, right? Here's a simple SQL table. Each entry has a series ID, which is just text, a timestamp, which you can store as like an int64, double precision float for the values, right? Because all of your metrics are just timestamp float, and then you make the series ID and the timestamp the primary key. And this will work, right? You'll be able to store data in this thing, but it's not going to scale very well. You're not going to get very high write throughput, right? You're going to be kind of fundamentally limited by the fact that Postgres or MySQL use B-tree indexes, and every time you're inserting data, you're writing these huge 4K pages, and you're not going to get very good compression. And there are better ways to do this. There's like much smarter ways to store time series data in traditional kind of relational systems, but still, at the end of the day, you're going to get bottlenecked pretty quickly. Next, before I kind of dig into the details of how this prototypes work, I want to explain a little bit about FoundationDB. So if you're not familiar, it's a distributed database, although it's very kind of, the API for it is very primitive. There's no query language. The only semantics it offers are key value storage. So all your keys can just be arbitrary byte arrays. All your values can be arbitrary byte arrays. It's kind of like Redis in that sense. except minus all the like sophisticated data structures. And then all the keys are sorted lexigraphically, which means that, if you insert keys that are, AB1, AB2, AB3, AB4, conceptually you can do range queries over those values in a fairly efficient way. Kind of one of the more interesting features that I think a lot of the databases that have similar semantics don't do very well is it has automatic detection and redistribution of hot ranges. So if just kind of the natural shape of your data is that data tends to cluster in certain time lexicographic orders for periods of time, FoundationDB will eventually detect that and kind of repartition the space so that data gets moved around to different storage nodes. If you've ever used systems like Cassandra or something like that that don't do this, if you end up in a situation where you have a hot partition, it can be very, very painful to solve. The kind of most important thing is it gives you completely ACID transactions at the highest level of isolation, so strict serializability. So this is kind of the same guarantee that you get like from a system like Postgres running at the strictest settings. And it turns out that these four things, they don't seem like much. It's like pretty raw. It's like almost like having like a hammer, but it turns out to be like a really good foundation for building distributed systems. And if you look at a lot of like commercial distributed systems out there, CockroachDB and yell me if I'm wrong, FaunaDB and a lot of other ones, or not Fauna, sorry, TiDB and a few other ones. A lot of them turned out to be like the fundamental layer at the bottom is a distributed transactional KV store with a lot of like really, really sophisticated logic in front to kind of mimic a SQL interface or some other kind of query language. The other thing that I really liked about FoundationDB and kind of why I started playing around with it is that like implementation really matters. And if you ever go read about the development of FoundationDB or play around with it in general, you'll just kind of immediately notice that a lot of care and like sophistication went into it. So for like first 18 months of development, FoundationDB was not designed to write to disk or write to the network. They have this like really crazy simulating harness that the whole thing runs in, where they can use to inject faults. The whole thing is like written in a custom C++ superset, I think called Flow, that implements this kind of Erlang style actor semantics. It's all kind of single threaded, shared nothing. So if you run like FoundationDB on a computer with 32 CPUs, then you'll end up running 32 independent FoundationDB processes that behave as if they're all running on independent machines, even though they're all on the same one. If you're at all like a storage geek, there's a lot of interesting stuff in there. Cool. All right, so what was I actually trying to accomplish with this? The goal was, again, I work on this distributed time series at Uber called M3DB, and the goal was, how much of M3DB could I replicate on top of FoundationDB if I was starting today? And kind of build something with a similar API, similar performance characteristics, and, equivalent compression. Because when you have this much data, the compression turns out to be super important. And kind of alluding to what I was saying earlier, the three big requirements are horizontal scalability, efficient compression, and really high write throughput, because that's what we care about with metrics. So the first thing I tried to do was just do the most naive possible thing you can do with a KV store, where every time you want to write a metric, you just write literally a tuple of the time series ID and, wow, this is like really small, I'm sorry, the time series ID and then the timestamp, like that's the key. So it's like series foo1, timestamp 0, series foo2, timestamp 1, and then the values are just the float values. If you can kind of imagine, this gives you like really terrible compression, right? There's basically no compression at all. You're repeating the time series each time. The write throughput is really terrible because at the end of the day, like, as efficient as something can be, distributed transactions are still fairly expensive. So on my laptop, this would only do like 5,000 writes per second, and you generate all kinds of disk activity because you're constantly trying to clean up this B tree. So that was, obviously not going to work, but it's always good to try the naive thing first, so you have a benchmark. So next thing I decided to do is like, okay, I'll just add the compression, right? So I already know how to do metrics compression. M3DB uses something called Gorilla compression, which is a compression algorithm that kind of came out of a paper released by Facebook. I'm not going to go into the details, but it's kind of like this streaming compression. But the tricky thing about Gorilla compression is that a lot of the times, if you're writing basically the same values over and over again, that compresses down to a single bit. So you need something, you have this compression algorithm that's like, okay, you want to write this value, you just encode the next bit as like 1 or 0. And trying to do that over an interface that's only allowing you to write key value byte slice pairs is really tricky. I kind of did it anyways though, just to see if it would work. And what I did is, Gorilla compression is basically, it's very stateful. As you're writing one data, the next data point, the last data point, and you use that information to kind of encode the next bit as you chug along. So what I did is I basically stored the mutable state of the encoder in FoundationDB. And then every time I wanted to do a write, you'd rip out the state, rebuild this in-memory state of the encoder, encode the next value, and then put the state back in FoundationDB. If you're wincing, because that sounds like it's going to be really slow, it was. So I had kind of the same problem where terrible write throughput, but the compression works. So at this point, I kind of realized there wasn't going to be an easy way to do this, and I'd have to build something a little bit more sophisticated. And so what I decided to do was just try and replicate M3DB's architecture as much as possible. But instead of kind of using raw disk APIs, where you interact with the file system, I was just going to treat FoundationDB as my file system. So this is how M3DB works, kind of oversimplified, but data comes in, right? You have metrics coming in constantly for all of your time series, and then two things happen in parallel. The first thing is the data gets stored in memory in like a in-memory mem table, very similar to how Cassandra and other kind of highly write-optimized databases work. And that's kind of buffered and compressed in memory. And at the same time, the uncompressed value is written to M3DB's commit log. So the commit log is there so that if an M3DB node fails or crashes, when you turn it back on, it can read all the data that hadn't been flushed as compressed data and rebuild the in-memory state. So once it's been written to the commit log, the write is like durable. You'll be able to recover it if the node crashes, and you can respond to your client with a success. And then kind of in the background, M3DB is constantly scanning through all the compressed blocks in memory and then flushing them to disk as kind of well-structured files on disk that can be like kind of scanned and sorted through when you need to satisfy a query. And yeah, so in that way you can ingest a lot of data, and at the same time you can slowly compress it over time. So it's very similar to how Cassandra manages like mem tables and SS tables, where the in-memory buffer is the mem table and the on-disk stuff is the SS table. And then if you think about where does your data exist at any point in time when you're using something like M3DB, so data that's really old that you wrote like hours ago maybe exists in these immutable file sets that are optimized for reads. And then the data that's more recent that you acknowledge most recently lives in two places at the same time. It lives in your in-memory mem table in the mutable buffers, and then it lives in your commit log files so that if the node dies and you lose everything that's in memory, you can rebuild it. So this is kind of how I decided to, redesign this thing thinking on top of FoundationDB. If this doesn't make any sense, that's fine. I'm going to kind of break it down and go through it in pieces. But the key takeaway here is it looks very similar to the M3DB diagram. Like you have an incoming write, it gets compressed in memory, and similarly at the same time written to a commit log, except in this case, the commit log lives in FoundationDB. And when the process is running in the background and taking your compressed in-memory blocks and writing them out to disk so that they can be fetched and evicted from memory later, that's also going to FoundationDB. Of course, we're not using files now, we're using FoundationDB's interfaces of sorted key value pairs. And I'll go into the exact format of the keys and values in a second in terms of data modeling. So this is where things start to get tricky. If you think of M3DB as a stateful system, right? If you're trying to run it in the cloud or on Kubernetes or something, like if a node dies and the commit logs live with the node, then when that node comes back up, it needs to read those commit logs, right? It's very stateful. Everything lives on the machine that ingested it. This thing's a little bit different. I call it quote unquote like a semi-stateful system. So there is state, and it is stateful, but the state doesn't live on the node that owns that state anymore. It all lives in this other system called FoundationDB. So that's what I'm calling these like semi-stateful commit logs. So when you think about your commit logs, right, there's a couple of things that you need to do. One is that you can't write every data point that comes into your system directly into FoundationDB as a commit log entry, right? Because then we're just going to run into the same problem I ran into earlier where I can only do about 5,000 transactions per second on my laptop. So what you do is you accumulate a bunch of writes in memory together into a chunk. You wrap that all up into like one kind of big byte array, and then you ship that off to FoundationDB as a single commit log entry. So you can say, commit log 0, commit log 1, commit log 2, commit log 3, and each of those will have a few hundred to a few thousand individual writes. And the commit log entries are optimized to be read from start to finish, right? You can't go to FoundationDB and try and look up data in the middle of your commit logs. They're only there to recover state when your node crashes and it needs to come back up and rebuild its mem tables. And so the two operations that you need to be able to support on these commit logs are, one, I need to be able to fetch all undeleted commit logs. So this is the operation I need when the node restarts and it wants to stream all the data back. And then the second thing you need to be able to do is you say, I have commit log entry 5. I need to be able to delete all commit log entries before that one. So commit log entries 1, 2, 3, and 4. And then just in terms of how I formatted my key, I just use monotonically increasing numbers. So it goes commit log 1, commit log 2, commit log 3. This turns out to be really easy, again, because you have transactions. So implementing a monotonically increasing number is not hard. The tricky thing then that happens with your commit logs is that you're writing a lot of them, right? If you think about, let's say you're doing 500,000 commit log writes or, data point writes per second, and those are all getting flushed to FoundationDB as commit logs, you're going to accumulate a huge volume of data really quickly because that's all uncompressed. So you need to be really smart about how you clean up these commit logs. One, just so you don't run out of disk space, but two, so that you don't delete data before it's been persisted in some other way, in which case, you violated your correctness guarantees. So the basic idea for cleaning up your commit logs, right, is let's say you're on commit log 3. You can wait for commit log file 4 to be written out. And then once commit log file 4 has been written out, if you then go and flush everything that you have in memory to some other durable format other than the commit logs, then after that completes, it's now safe to delete all commit logs before commit log 4. And you can basically run that in a hot loop. It's where you basically wait for a new commit log, flush everything that's in memory, delete all the commit logs that existed before you started the process. So that's what it looks like in code. It's pretty simple. You basically, there's a commit log system, and you'd say, wait for the next commit log file to come back. It gives you like a token that tells you which commit log was just written. Then you flush everything that's in memory. And then you go to the commit log system and you say, okay, I've now flushed everything in memory. Here's the token you gave me earlier. Go and delete every commit log entry before that because I don't need them anymore. And that just kind of runs in the background. So are we a database yet? Not really, right? All we can do is write commit logs, clean up commit logs, and read commit logs. We still can't really satisfy any read queries, right? Except for data that's in our mem tables, but that's only a very small percentage. So the next thing that you have to do is you have to implement kind of like a buffering system, right? And this is where the concept of building a semi-stateful system in front of another kind of strongly consistent system comes into play, where you do this buffering in front, and you're basically doing the same thing that systems like Cassandra do, where they buffer a bunch of data in memory in these mem tables, and then asynchronously flush it to durable things called ESS tables. And so you have this thing called the buffer, and when you flush stuff to disk, you can either choose to merge it with an existing chunk to build one bigger chunk, or you can flush out a new chunk so you don't end up with these huge pieces of data. And both your reads and your writes have to flow through this thing, right? So every time you write, you have to include it in memory so it can be immediately read afterwards. But when you do a read, you also need to merge across everything that's in your memory system, but also whatever has been sent to FoundationDB. And that allows you to basically read your writes. So conceptually, the buffer is like pretty simple. This is more or less kind of what it actually looks like. It's basically a synchronized hash map, where the key in the hash map is the name of your time series. And then the value is a slice of Gorilla encoders, right? The things that are actually doing the streaming mutable compression. And I'll explain why it's a slice or an array in a second. I'm not going to dig into this code. This is like really small, but basically this is the write pathway. But the write pathway is really simple, right? Basically what you do is you go into your hash map and you say, here's the time series I'm writing a data point for. And it'll return back a slice of encoders. And you pick the most recent one. The most recent one is always the quote unquote mutable one. And then you just encode the next value into that stream. And then you're done. The commit log writing is handled separately, but that's pretty much all you have to do on the buffering side. And if there's no existing encoders, then you just create one, insert it into the hash map, and move on. That part's really simple. The flushing is where it starts to get tricky, and this is where having the distributed transactions that you get out of a system like FoundationDB becomes really nice. I said before, right, the flush mechanism on the buffer has a very specific contract, which is that once the flush method completes, everything that is stored in memory in the buffer or the mem table that was present at the beginning must now be persisted durably in FoundationDB. So how do you implement that? Well, you basically loop through each series in memory. And then for each series in memory, you take the current encoder, you mark it as immutable, create a new one for subsequent writes, and then you take all of your immutable encoders and flush them to FoundationDB, where they can basically be read later. And I've been saying this a lot, like flushing data to FoundationDB in compressed form. And I've been glossing over some details. What does that actually mean, right? Because anything you put in FoundationDB that's not a commit log has to be easily readable, right? So this is what it looks like. For each time series in FoundationDB, there's a couple of entries. There's one metadata entry, and this is somewhat inefficient and you can make it better, but for this version, I just use one metadata entry. And then there's a bunch of entries for all the different compressed blocks. So what you do is there's this one metadata entry contains the name of the key. It contains basically just a slice of all the other chunks or data compressed chunks that exist for that series. And then for each chunk or piece of that time series that I've stored in FoundationDB, you store a path to its key so you can look it up, the first data point that it contains, the last data point that it contains, and then its size. So what I do is when you're getting ready to flush, the first thing you do is you go and you say, okay, I'm writing series foo. Give me the metadata for series foo. And then FoundationDB will come back and it'll say, okay, for series foo, you have 3 chunks. You have like chunks 1, 2, and 3. They contain data between these time ranges, and these are how big they are. And I'll look at those chunks that I have, and I'll say, okay, based on the metadata that I got back, this chunk is really small, and it has a similar time range to the chunk that I'm about to write out. Let's merge them together. So then you'll read that existing chunk, the one that kind of matches and is too small. You'll read it into memory. Then you'll merge the chunk that you want to write to FoundationDB with the one you just read out of memory. Then you'll write back the updated series metadata saying, hey, that chunk that you had before that's small, it's actually bigger now and the timestamps have updated. And then you also write back the new kind of compressed chunk that you just merged. And you can do all of this in a single ACID transaction performed with the highest level of isolation, basically that any database will give you. So like 100% for sure, like this is correct. Like you're not going to run into any weird edge cases where like your metadata store says you have this thing, but actually the data in FoundationDB looks different. And in this case, I'm storing the data in FoundationDB because it was easy. But you can easily imagine a database where the time series data actually exists in S3, right? Because S3 is really cheap. And it's only indexed in FoundationDB. But because I can update all of these different things transactionally, you can keep that stuff up to date. Okay, so that was the flushing system. The final thing is like, how do I actually do a read? And this is where the metadata comes into play. So someone comes in, they say, I want to read series foo. The UK, okay, series foo, let me go get the metadata. All right, I know for series foo that I have 3 chunks. So if I look at the first and last data point for each of those chunks, I can determine that only one of those chunks actually contains data for the time range that I'm trying to read. So I go fetch that one chunk. And then I also determine which in-memory buffers contain the data that I need as well. And then I just merge all of those chunks together to create basically an ordered list of all the values that were put into the system and can return that back to the user. So what this is done, so it's a lot more work than my first 2 implementations, but still significantly less work than building M3DB from scratch. And this thing actually fits the requirements pretty well. You get horizontal scalability. FoundationDB is like kind of a traditional distributed system. It scales horizontally pretty well, especially if you design your data in such a way that you have very little conflicts in your transactions. And this thing has almost 0 conflicts. You get fairly high write throughput. So on my laptop, this will do about 1 million writes per second. And you get really efficient compression, right? This does the same compression algorithm that M3DB does. So if you have data that looks like metrics data, you get like 8 to 11x compression. So we got all 3. This isn't really a real time series database though. It's kind of just like a dumb metric store. To really kind of build something interesting around this, you need the ability to index your data, right? You need to be able to say like, okay, I want to look at all the time series that correspond to the P99 latency across any of my services or all of my endpoints for this service, right? That's where things get a little bit more complicated when you're using something like FoundationDB. I probably am going over a little bit in time, so I'm going to leave this part out, I think. If you're curious, I'm going to link to a blog post at the end of this talk. You can go read about it in a little bit more detail there. But there are ways to do it. Okay, so kind of in conclusion, building a semi-stateful system like this in front of a distributed system like FoundationDB is a lot of work, but it's a lot more work than building like a stateless one. But it's way less work than building something from scratch, like a lot of people do. And for 2,000 lines of Go code at the very end, I mean, it took me a little while to get this going because I was learning about how FoundationDB works, but the end result is about 2,000 lines of code and you're doing millions of writes per second. To actually productionize this into like a real system you could use and like sleep well at night, you'd probably have to 10 to 100x the amount of code here, but it's still orders of magnitude less than doing something from scratch. Yeah, so you're never going to beat a purpose-designed storage system doing this, but it's much easier to program against than the operating system, the file system, the network, the physical hardware. At no point did I have to think about like aligning my data to page sizes. I didn't have to think about like the fsync syscall and what that means and when I need to call it. There's just a million things you just don't have to worry about when you build on top of something like this. That's it. That's my email address if you ever want to talk. And that's the project. You can go read the code in the blog post. It's just a README.